Okay, we're continuing on here with chapter 8, I believe, gases. The last time we started talking about gases, and remember again, that is obviously a state of matter where everybody is flying around. And as we talked about, it is those collisions that occur as the gas molecules are flying around, as they have pretty good amount of energy associated with them, that causes pressure that we associate with gas molecules. In terms of pressure, there's several units that we commonly come across in this class, and it could be units of atmospheres, it could be units of torr, or it could be units millimeters of mercury. There are obviously other units, but those really are the three sort of common ones that we do come across. And there is a relationship between these. One atmosphere is 760 millimeters of mercury, and that is 760 torr. That also means a millimeter of mercury and a torr is basically a one-to-one relationship or conversion between the two. And that 760 number is an important number, as we talked about last time, to go between the units. So if you do have atmospheres and want millimeters of mercury or torr, you're going to multiply by the 760. The atmospheres will cancel, leave you torr. Got brighter. And if you are starting with torr or millimeters of mercury, we would be dividing again by the 760 here, and that would get you to atmospheres. We talked about some gas laws here, and when we talk about gas laws, there's usually sort of three variables that we deal with, and that is pressure, volume, and temperature. And in a lot of cases, we may again keep a couple of these things varying and one constant, or we may keep all of it sort of not constant. So we talked first off about a couple of gas laws. We talked about Boyle's law. Boyle's law looked at the relationship between pressure and volume, and that is P1 V1 is equal to P2 V2. This is at constant temperature. And in this particular case, the relationship that we saw or talked about was basically as one went up, the other went down. So in this case, as the volume gets really small, that's going to mean that the gas molecules really don't have a lot to basically really all right. So as the volume goes down, we're going to have a lot more collisions that's going to occur, and that's going to increase the pressure. And because they're in a very small space, so they don't have a lot of room, more collisions, and vice versa, the pressure will start to go down as the volume does start to increase here. Again, when the volume increases, gives it a little bit more room to fly around in, takes longer for collisions to occur, and that's going to obviously lower our pressure. In terms of units, it doesn't really matter the units here as long as they are the same units on both sides. So as long as the two pressures are the same units, as long as the two volumes are the same units, then you can put any type of units you want into here. We then looked at Charles' law, and he dealt with volume and temperature relationship, which is V1 over T1 is equal to V2 over T2 here. This would be at constant pressure. And the importance here in any sort of gas law, the temperature always has to be in Kelvin. So that's just a must, and always has to be in Kelvin when you go into the gas laws. So our temperature in Kelvin, once again, is the temperature in Celsius plus a 273 is again how we do that conversion. In terms of the relationship that we see for Charles' law, we see that as the volume goes up, so does the temperature. And as the volume goes down, so does the temperature. And as we talked about last time, is that adjusting in the temperature, adjusting in the volume that allows it to maintain constant pressure. So what happens is when we increase the temperature, the gas molecules are flying around a lot faster and would cause a lot more collisions. So what the system does is the volume basically expands. And when it expands, it takes the same amount of time, basically, for those guys to have those collisions because they're in a much larger volume. So it's actually the adjustment of the volume here that allows the pressure to remain constant It really allows the number of collisions to remain constant, which is why the pressure remains constant here. And that's different than Guy-Lussac's law, which is very similar, which is P1 over T1 is equal to P2 over T2. And once again here, we do need our temperature in Kelvin. And by the way, for Charles' law, the volume doesn't matter. Again, could be any unit of volume as long as they're the same. Same thing here with the pressure. Pressure could be any unit you want as long as they're the same on both sides. The relationship that we see here is, by the way, this is at constant volume. So the volume here is not going to change in this situation. So the relationship that we see is as the temperature increases, so does the pressure. So we have sort of the opposite situation than happens in Charles' law. In a sort of Guy-Lussac's law, because the volume is fixed, it doesn't move. When we increase the temperature, our gas molecules will fly around faster. And because they're in the same amount of space, we're going to have more collisions than we did before. And that's going to create the pressure to start to increase. And vice versa here, if we lower the temperature, the pressure will also start to lower. So again, the volume will stay fixed. And as we lower that temperature, they're moving slower. So it's going to take a little bit longer for the collisions to occur. And that will basically allow the pressure to start to come down. Any questions on any of those there that we talked about? Reminder that a lot of these do require sort of solving for one thing that's missing. So rearranging these equations. So in general, as we talked about, a quick way to rearrange things is, you know, if it's on top on one side, if you move it to the other side, it'll end up on the bottom. Or if it's on top on the other side, it will end up on the bottom. Or vice versa, if it's on the bottom on either side and you move it across the equal sign, it will end up basically in the opposite location. So that's a quick way to kind of rearrange an equation. Just move it to the other side and put it in the opposite spot. Again, if it was on the top, put it to the bottom. If it's on the bottom, put it to the top. And it's a kind of a quick way. Any questions on any of that stuff there? All right, so why don't we try one here? I think where we left off. In an experiment, 452 milliliters of a gas is used for a light bulb. It goes from 22 degrees Celsius to 187. What is the final volume here? So take a moment or two and see what you come up with. All right, let's take a look. So as I mentioned before, you know, there's a number of gas laws, obviously, we are learning here. So we could run through the list here. Boyle's, we got Charles' law, and we got Guy-Lussac's law right here. So a very good approach to sort of gas law problems, if you're not really sure maybe where to begin, is really just pull out the information, label what it is, and it oftentimes will point you to sort of the right place. So obviously we have 452 milliliters, which is a volume. We have 22 degrees, which is a temperature. We have another temperature that's a 187, and we are looking for a volume. So pretty quickly, you should be able to eliminate these two guys, and you could probably almost see Charles' law kind of there in our listing there. And obviously that would be the correct one to sort of choose. Again, in terms of ones and twos, it really doesn't matter which side it ends up on as long as the numbers that go together stay together. So I'm just going to call these guys one on this side here and call these guys twos. Now, I do need to do a couple of things here, and that involves the temperature. So once again, it does need to be in Kelvin. And even if, as I mentioned, I think last time, they give it to you in Celsius and want the answer in Celsius, you still need to put it into Kelvin to go into the gas law. So we're going to add 273 to this guy, and that will get us 273 plus a 22, 295 Kelvin. We'll also add a 273 to this guy, and that'll give us 187 plus a 273. Looks like a 460 Kelvin. Now, in terms of units of our volume, it doesn't really matter. All this means is when I do solve for the volume here, it's going to end up being the same unit. So it'll end up being milliliters when we're all said and done. So we'll take our V1 T1 equals V2 T2. In this case, we are looking to solve for V2. So that means we do need to move T2 to the other side. So again, the quick way is it's on the bottom. So it's going to end up on top when we move it over. And that would give us V1 times T2 divided by T1 equals V2. We are basically multiplying T2 to both sides. It's basically mathematically what we're doing. We're multiplying the T2 basically to both sides. Any questions on that there? Now, the other important thing with gas law problems is to make sure you do get the right numbers in the right spot. So it's very common people sort of invert numbers and put them, the ones for the twos and the twos for the ones. So in this case, our V1 would be 452. Our T2 should go up on top, which is 460. And our T1 should go on the bottom, which is 295 Kelvin. Here, the Kelvin and the Kelvin will cancel. That's going to leave us milliliters, which is good because we are looking for a volume. So we're going to take a 452. We're going to times it by a 460. We're going to hit equals. We're going to then divide by 295 and hit equals. And we're going to end up with 705 milliliters in this case. Any questions on that calculation there? Now, again, understanding some of the relationships can be helpful to make sure, it does sort of make sense. So what we do see here is the temperature was 22. The second temperature was 187. That means that the temperature went up. And because of Charles' Law's relationship, we would expect that the volume would go up. And it did. It started at 452 and ended at 705. So again, that fits the sort of reasoning we would expect to happen here with a Charles Law sort of situation. Any questions on that there? All right, so in addition, there is another sort of law that sometimes comes across, so why not? We'll talk about for a second here. That is Avogadro's law. He had a number, but heck, he wanted a gas law as well, so why not? So Avogadro's law deals with, if you wouldn't be surprising, moles actually. So Avogadro's law is V1 over N1 is equal to V2 over N2. And this is actually at two things. This is at constant pressure and temperature. So at constant pressure and temperature, this relationship happens. The V's here are volume, and they could be any volume unit you want, milliliters, liters. The N here are actually moles. So N is moles, which is like what we would expect to happen with Avogadro, which is all about moles. So N is the number of moles. And basically you could kind of plug and chug into this like any other equation. If you got a couple of volumes, you can find a moles or vice versa as well. The relationship with Avogadro's law is basically as the volume increases, so there's like the moles. So the moles sort of increase proportionally to sort of the volume as it increases. So that's another gas law that might pop up somewhere along the way. And again, you use it like any other to solve for one of the three things that may be there. Now, taking together all these gas laws here, which is Charles' law, Boyle's law, and Avogadro's law, we do get the granddaddy of them all there, which is the ideal gas law. And the ideal gas law is PV is equal to nRT. So there is a couple of differences between this gas law and some of the ones that we've seen before. Some of the ones that we've seen before deals with kind of like a before and after situation. You have two pressures, you have two volumes, you have two temperatures. Here with the ideal gas law, it is just basically one set of conditions. So you got one pressure, one temperature, and so forth. So it's not sort of a before and after situation. The other really important thing about the ideal gas law is it is also the most restrictive in terms of units. So when you use the ideal gas law, everybody needs to be in certain units for everything to cancel out correctly. So let's talk about those units. For pressure, it absolutely has to be in atmospheres when you use the ideal gas law. For volume, it has to be in liters when you use the ideal gas law. For N, which is moles, it should surprisingly be in moles. So it definitely should be in moles. And much like all other sort of gas laws, our temperature does also need to be in Kelvin. So these are the specific units that they absolutely have to be in when you use the ideal gas law in order for everything to work right. The real reason for that is R is the gas constant, and it is a constant value that we typically use. So R has a value of 0.08206. And it also has all those units is liters times atmospheres on top, Kelvin times mole on the bottom. Now, some people use a rounded version, which is fine, 0.0821. I personally usually use this number because that's what they beat into my head, and I just can't get it out. But a lot of people nowadays will use 0.0821, which is perfectly fine to use for that. The other good news is you probably will have R given to you, so it can remind you if you forget what everybody's units should be. So that basically will tell you what everybody else in that equation or formula units should be. They should match those units that go with R. What is an ideal gas? An ideal gas is essentially pretty much what we assume any gas is. And there's a couple of things that make something an ideal gas. One thing that makes something an ideal gas is the idea that the volume of the gas itself is relatively small versus the container it's in. So a lot of times in an ideal gas and a lot of situations when we do problems, we oftentimes talk about not really the volume of the gas itself, but the volume of the container at which is flying around as it fills it uniformly. And basically the volume of the gas in an ideal situation is really negligible, and it's really more the volume of the container at which is flying in is what we kind of look at it. The really other thing that's truly what kind of makes it a little bit more of an ideal gas is the idea that if you have multiple gas molecules in a container together under ideal situations, which is pretty much every situation we deal with in this class, they will have no effect on each other. So they won't be attracted to one another. They won't be repelled by one another. It's almost like they are flying in the container by themselves, even though there's other gas molecules flying around with them. And that's one of the ideas of an ideal gas. So you could actually have multiple different gases in the same container flying around, and we could kind of treat it like they're in there by themselves, even though there are other gases in there. So that's the other part that makes something an ideal gas is there's no attractive or repulsive forces between gas molecules. So basically, we think of them as just kind of doing their own thing and not really affected by any other gases that are in there, and they don't affect any other gases that are in there. And that's what happens in an ideal situation, which is pretty much what happens under normal pressures and temperatures that we deal with in this class. When you get to really high pressures and really kind of low temperatures as well, those things you do actually have to take into account, and you sometimes hear people talk about real gases, which aren't like these fake gases here. Now the real gases, you do have to take those into account, but we don't deal with that here. We deal strictly with ideal gases. You could assume an ideal gas in every situation. And the nice thing about that is you could use the universal ideal gas law in pretty much that situation if you needed to solve for something. A couple of other important sort of words and things that we come across are this. We'll start with STP. STP stands for standard temperature and pressure. So when somebody says at STP, they're actually giving you a pressure and a temperature. The pressure is 1 atmosphere and the temperature is 273 Kelvin. So when it does say at STP, or this was done at STP, or what is the volume at STP, they're basically giving you those two things: 1 atmosphere for the pressure you should use, and 273 Kelvin for the temperature. There is a really nice relationship that occurs at STP, and you can only use it at STP. So if you happen to be at STP, 1 mole of any gas will have a volume of 22.414 liters. So that is a conversion that can allow you at STP conditions not to have to use the ideal gas law. You can kind of bypass the ideal gas law and just kind of do a little conversion. But again, 100% to use that relationship, need to be under STP conditions. So if the pressure is not 1 atmosphere and the temperature is not 273, you should not use that relationship at all, specifically only for STP conditions. The good news is you can use the ideal gas law for any condition you like. Non-STP conditions, STP conditions, you could just throw everything into the ideal gas law and you'll get the right answer as well. But sometimes it can sort of save you a little bit of time to use this under those STP conditions, but you definitely do not have to. If we take the ideal gas law and solve for R and then pretty much put everything in under STP conditions, that is basically where we get the gas constant from. So that's basically where the gas constant comes from, is using at STP conditions, we would have 1 atmosphere and 273, and it would have a volume of 22.414 liters and 1 molar. All right, so let us try one here. Calculate the pressure exerted by 1.82 moles of SF6 gas in a volume of 5.43 liters and 69.5 degrees Celsius. In this case, we are looking for a pressure. We have 1.82 moles, which is an N. We have a volume that is 5.43 liters, and we do have a temperature that is 69.5 degrees Celsius. So again, if you sort of run through your list, you could probably see the ideal gas law there, but obviously this one would not work. We don't have 2 pressures, don't have 2 volumes, don't have 2 pressures or temperatures. We do have moles, but we don't have 2 volumes. So really, again, this would be the only one that would make sense. Remember that although it is not normally given to you in the problem, you always have R available to you. So once again, they typically will not give it to you in the problem. So that's just a number you got to think in your head that, you know, you just have available to you to use, as it is a constant. And if we just kind of go through our PV equals nRT, we are looking for a pressure. We do have a volume, we do have moles, we do have R, and we do have T. That means we do want to solve for pressure here. And again, although this is not written as a fraction, if you want to do, again, the quick way, you could think of it as being up on top, which means when I take my volume to the other side, it's going to end up on the bottom over there. And that would give me that P is equal to nRT divided by V. We're basically dividing both sides by the volume in this case, yeah. At this point, we want to put everything in, but remembering this is the most restrictive, so moles are good, our volumes in liters, so that's good. So it is still our temperature here that we do need to do a conversion for. So our temperature would be 69.5 plus a 273 to convert it into Kelvin. That gets us plus a 273, 342.5 Kelvin. Now we have everything we need, so we'll go into our equation here. Our moles was 1.82. We'll put our R in there. And we'll put our temperature, 342.5 Kelvin. That's all going to be divided by our volume, which was 5.43 liters. In terms of the units here, my liters on the bottom cancel the liters there in the gas constant. My mole on top cancels the mole in the gas constant. My Kelvin on top cancels the Kelvin in the gas constant. That is going to leave us atmospheres as the only unit left, which is good because, again, that is a pressure, and that is what we're looking for. So 1.82 times 0.08206 times 342.5 hit equals, divide by 5.43 gives us a pressure of 9.42 atmospheres. Any questions on that equation there? Now, variation of this is you may be given not the moles, but you may be given grams. So a very common thing is you got to convert grams to moles. And as we talked about that is the molar mass, again, that you use to convert grams to moles. So that's a variation of a problem. That's very common that you might have to do. So it may not just be given to you in moles. It's very common. You got to go grams to moles And the molar mass from the periodic table, again, is what we use to do that, like we talked about earlier. Any questions on any of that there? Yeah, so remember when we do temperature conversions, and just specifically temperature conversions, if all you're doing is changing the temperature from one unit to the next, you want the converted number to look like the original number. So in this case, the original number went to 1 decimal place. So you would probably not round in this case. You would actually keep the 1 decimal place in this case. Yeah. Other question? And that's that kind of specific rule that's just for specifically converting temperature. Yeah. Other questions? And the overall answer, I'm not sure it made probably a big difference if you did round or not, but yeah. So, but typically speaking, you probably shouldn't in this particular case. Yeah. Other questions? Yeah. Do you do anything with the SF6 gas? No, it's just telling you what gas it is. It's like, so sometimes it's kind of like, I think we had a problem earlier, right? There was something like kilometers in there or something, right? So sometimes there's some extra information that you don't actually need to use in this case, which is actually just telling you what type of gas it was in this case. Yeah. Other questions? Yeah. So let us continue on, because I feel like we don't have enough gas laws. So let's add a few more to them. You're welcome. I'm here all week, twice a week, two shows daily, I suppose. That's a lot of questions. It actually is, I think, on. No, we don't have an exam this Wednesday, right? Next Wednesday. I think our exam is 2 weeks from today, I think, right? Yeah. We do have quizzes next week, yeah, if I'm not mistaken. So we do have some quizzes, but that's chapter 6. So to answer your question, I do believe it is 6, 7, and 8, which is this one. Yeah. Okay. Yeah. Okay. So you're scaring me like I gotta go write an exam or something. I'll be right back. Let me go write it. No, but I believe it is on this second exam, if I'm not mistaken. Yeah. Okay. Now that my heart started again, we are going to talk about changes in pressure, volume, and temperature. So there is sort of a relationship that actually deals with all 3 sort of variables together. If we solve for an ideal gas life for R, since they are the same value, we could set them equal to each other. And really, as long as you don't open the top of the container, you probably shouldn't lose gas out of it, which means typically the moles stay constant. So this equation here is sometimes referred to as the combined gas law. And it deals with all 3 variables together. P1 V1 over T1 is equal to P2 V2 over T2. And really here, pressure and volume can be any units of pressure and volume. Again, as long as they are the same on both sides. But like everybody else here, once again, the temperature does need to be in Kelvin in this case. So this is the one that sometimes people have a little trouble rearranging. So once again, just kind of move it to opposite locations can be very helpful to rearrange it. This is also a pretty good one. You think about sort of the gas laws that we've been talking about here, and the number of different gas laws. So we had up until this point, P1 V1 is equal to P2 V2. We had V1 over T1 is equal to V2 over T2. We had P1 over T1 is equal to P2 over T2. And we had a couple of other ones here, but not too worried about Avogadro and our ideal gas law. So this one that we just learned is actually a pretty good one to help you pretty much remember the others. So if you just want to learn one gas law, learn this one. Yeah. So if you learn this one here and you have a problem where it says the temperature is constant or there is no temperature given to you, you basically just scratch out the temperature and there's Boyle's law. Yeah. Now, if you remember this one here, which again is the same one, and you come across a problem where there's no pressures given to you or pressure says it's constant, you just scratch out pressure. And there's Charles' law. Yeah. Now, if you take P1 V1 over T2 is equal to P2 V2 over T2, And you see that there's no volume there. You just scratch out the volume. And there is the other one. So this is a really good one if you just memorize this one and just take out the thing that's not there. And you'll have all the other ones pretty simply memorized. You're welcome. All right. So honestly, you probably don't have to worry too much about Avogadro's law, but you can actually get it from this as well if you put the ends in there. But so the other one would be this one, and I would recommend learning this one. And once again, remembering all you got to do is take out the thing that's not there, and you'll pretty much have the gas law that you need pretty easily. Any questions on how to do that there? Yeah. All right. Free tips, and there you go. So let's try our rearranging skills here, shall we? Consider a sample of oxygen gas at 27 degrees Celsius with a volume of 9.55 liters and a pressure of 2.97. You decide to change pressure to 8.25 and also heat it up. What is the new volume? All right, put those math skills to use. I will do it as well. Although my math skills have not been great today, but I'm going to try here. There you go. Look, hey, earlier today, I took like 5 minutes to try to say a number. I was staring at the calculator here, and I kept saying 1 point something, and there was like no one on it. It was like 0 point something. Finally, people had to yell up like, hey, it's like 0.02. I'm like, okay, let's see how we're doing. So once again, I'm still going to pull out the information here. I got a temperature that is 27 degrees Celsius. I have a volume that goes with that of 9.55 liters, and I have a pressure that goes with that of 2.97. I then have a new pressure there to 8.25 atmospheres. I also then have a new temperature to 125 degrees Celsius and a volume that I'm looking for. So once again, if you sort of see what's there, hopefully the combined gas law there, which is the only thing, as the problem disappears, is the only thing that has obviously all three guys involved in it. So in this case, we could again call the guys on the left here all ones, call these guys all twos, just to keep some numbering. In this case, we have everything but V2. So we are looking to solve for V2. That means in this particular case, we actually need to move to the other side, both P2, right, and T2. So the P2, which is on top, will end up at the bottom, and the T2, which is at the bottom when it goes to the other side, will end up at the top. And that would give you, if you rearrange this correctly, P1 V1 T2 divided by T1 P2 is equal to V2. We are mathematically multiplying T2 to both sides and then dividing by P2 to both sides. And we end up with what we get there. Any questions on that there? Now, we do need to do a couple of things here. Pressure on both sides are good. They're both the same unit, so that's okay. As usual, our temperature needs a little work, so we're going to do a 273 on that, and that should give us a 300 Kelvin. We're also going to add a 273 to this temperature here, which gets us a 398 Kelvin. And now at this point, we really do have everything that we need. We just got to make sure everybody gets in the right location. So here up on top, we want P1, which is 2.97. We want V1, which is 9.55 liters. And here we want T2 up on top, which is 398. So it's really important to rearrange correctly because people always get the temperatures and stuff in the wrong spots. We're going to divide by T1, which would be 300 Kelvin on the bottom, and P2, which would be 8.25 atmospheres. Our atmospheres on top and bottom will cancel. Our Kelvin on bottom and top will cancel. That's going to leave us units of liters when it's all said and done as our answer. And that answer will be a number with a unit of liters. Remember, in this case, you might want to hit equals each time and divide by each number separately on the bottom. And that will give us an answer of 4.56 liters. Any questions on that one? So again, remember, we got multiple things there to multiply and divide. You can do all the numbers up on top, multiply them all, then hit equals. Divide by 300, hit equals, and then divide by 8.25 and hit equals, and you should get that number. Yes. Any questions on the combined gas law here? Probably the one that gives people the hardest kind of rearranging, but it is very useful. As we just saw, you can pretty much get all the other gas laws from it, so it's a good one. If you got to put your money on one law, remember that one, and the ideal gas law is a good one as well. Those two. Any questions on that there? Okay. All right, the next thing we're going to talk about is actually partial pressures, Dalton's law of partial pressures, and it sounds very complicated, but it's actually not too bad. Oftentimes gases do come as mixtures of gases, so you got a bunch of gases floating around in the same container. And when we have just one gas by itself, for example, if I just had gas molecule A in the container and it's flying around, pretty much the total pressure of this container is a result of pretty much just the pressure by gas A. Now, if I take another container and I put it in gas A and gas B and gas C flying around, now the total pressure of this container is really a result of all three gases that are present. They are all contributing to the total collisions that are occurring. And the total pressure here would be the pressure of gas A plus the pressure of gas B plus the pressure of gas C. Because they all are contributing to the overall pressure of this mixture, they are partially contributing, which is why they are referred to as partial pressures, because each one is partially contributing to the overall pressure of the entire mixture. So what is a partial pressure? It frankly is PV equals nRT. Yes, that's basically what it is. PV equals nRT, the ideal gas law. Where you solve for pressure, nRT over V. This is a classic case of where the ideal gas comes into play. In a mixture of gases, even though we got a bunch of different gases flying around, because they are all ideal gases, this is like a place where we could go, I don't really care about each gas together. I could look at each gas individually and think as each gas is in that mixture by themselves. So what that does is it makes you able to use the ideal gas law in my example here for each gas separately. So you could do the ideal gas law in my example here 3 times, one for gas molecule A, one for gas molecule B, and one for gas molecule C. Now, there's a couple of good things about them all being in the same container. One good thing is the volume of this container is the same for every gas that's in there because they're all flying around in the same place, basically. And there's a very good chance that that container is sitting in the same room. That means the temperature is going to be the same for all the gases. So if you think about this, the T will be the same for everybody. The V will be the same for everybody. R is a constant, which is the same for everybody. So really in these type of problems, the only thing that's going to be different is how many moles of each gas you have. So a lot of times, the only thing that you need to figure out is how many moles of each of the gases are there. And a lot of times this will require the grams to mole calculation that we talked about using our molar mass. So basically what you would do is you would use the ideal gas law separately for each gas. You would get a pressure for each gas, which would be the partial pressure of each of those gases. And if you wanted the total pressure, you would simply add all those numbers together. Yeah, so you would add all those numbers together, and that would give you the total pressure of that gas mixture. Question on that there. Now, in a textbook problem, that is how you would get the total pressure. In a laboratory situation, the total pressure is the barometer reading that you would take off the wall, is the total pressure in the room, basically. But in a textbook problem, this would be how you would calculate, obviously, the total pressure if it wasn't given to you, obviously. Any questions on any of that there? So one very common way that we do partial pressure problems is simply ideal gas law individually for each gas. And because they are ideal gases, we basically can do that and apply it that way, which is essentially what this slide says, I think. That's pretty much what it says. So again, basically we could do the ideal gas law for each gas separately, add them together. And you got 2 gases, you would do it twice. You got 3 gases, do it 3 times. You got 4 gases, do it 4 times. 4 different sort of calculations, and then add them together. So why don't we try one here, see how you do. We have 5 grams of helium. We got 5 grams of neon. They're in a 2.5 liter container at 27 degrees. We are looking for the partial pressure of each gas and also the total pressure. So helium from the periodic table, 4.003. And what's it, neon? It was neon, 2018. Neon is 2018, we'll call it, I think. Ish, maybe. All right, we're looking for 3 answers here. So in this situation, we basically have a container, and inside the container, we have helium flying around, we have neon flying around. And again, because it's really an ideal gas situation, we could assume that although they are in the same container, they're kind of in their own bubble. They're kind of like they're by themselves. So we do just want to kind of do an individual calculation for each of them individually, and that will give us the partial pressures of each gas. Once again, though, the volume for each of them will be the same. So it's 2.5 liters for both of them because they're in the same container. And because that container is in the same room, the temperature will also be the same for both of them. We are going to use PV equals nRT. And again, we're going to be solving for pressure. So that means we're going to take volume and move it to the other side on the bottom. And that will give us P is equal to nRT over V. We do need to do a couple of things here. First off, we always have obviously R, right? So that's again a constant value that you always have. We also, much like normal here, do need to convert our temperature into Kelvin, and that again should give us 300 Kelvin, I believe. Now we really have everything that we need to go into these equations except for N, which is the moles. So we do have grams of each gas. So really the first thing we want to do is get the moles of each of them so that we have what we need to go into the ideal gas law. Because again, if you just check it off, we have temperature, we have volume, we have R, but we are again missing the moles part here. So that's why we have to do that conversion of grams to moles. So we'll just do that real quick here. We got 5 grams of helium, just like we did when we were talking about moles and Avogadro's number and all that stuff, which you do not need Avogadro's number here. We're just going to use the molar mass, which is 4.003 grams per mole of helium. That once again is found from the periodic table. So that is where we find our molar mass, the number underneath the symbol. 5 divided by 4.003, 125, we'll call it. 1.25 moles of helium. We'll do the same conversion there for neon. So it'll be 5 grams of neon. Once again, going to the periodic table, we see it is 2018 grams per mole. Grams cancel. And for neon, that gets us 5 divided by 2018. Gets us an error. Let's try that again. Gets us 5 divided by 2018 again. Gives us a number. That's better. We get 0.0. No, too many zeros. Try again here. We get 0.248 moles. There we go. All right. So now that we have the moles of each of those guys, now we really do have everything that we need to go into the ideal gas law. So once again, we're just going to go into it separately for each one. So we'll do the partial pressure of helium first, and that would equal nRT over V. We're going to put in everything here for helium, which is really just the moles part. So the moles for helium was 1.25 that we calculated right there. Our R, which is our constant, 0.08206 liters atmosphere Kelvin mole. And our temperature, which is the same for everybody here, is 300 Kelvin. All going to be divided by our volume, which is also the same for everybody, 2.50 liters. At this point, the moles will cancel, the Kelvin will cancel, and the liters will cancel. That's going to leave us atmospheres left over. That means on top there, we're taking 1.25, we're timesing it by 0.08206, and we're timesing it by 300. We're hitting equals. We're then divided by 2.5, which gives us something like 12.3 atmospheres as our partial pressure. So this would be the partial pressure of helium. Any questions on that one there? We're then going to pretty much do the identical calculation for neon. And really the only thing that's going to be different is the moles of neon. So that's the only thing that will be different. So we'll go into here. We're going to use pretty much the same numbers through, but we will obviously use the correct moles here for neon, which is 0.245 that we calculated earlier. We'll use our gas constant. Again, it's in the same container, which means it has the same temperature, and it's in the same container, which means it has the same volume as well. Once again, here, the moles will cancel, the Kelvin will cancel, the liters will cancel, leaving us atmospheres, and taking 0.248 times 0.08206 times 300. It's equals divided by 2.5 gives us 2.44 atmospheres. And that would be the partial pressure of neon in this mixture. Any questions on any of those numbers there? Now, if I want the total pressure at this point, how do I get it? Yeah, we're just going to simply add the two partial pressures together. So our total pressure of this mixture of gases is the pressure that's applied from helium, which is 12.3 atmospheres, plus the partial pressure of neon, which is 2.44 atmospheres. And that gets you 14.7 atmospheres as our total pressure in this mixture. So it really is, in a lot of cases, if you have to do sort of a partial pressure situation like this, it's really just the ideal gas law, solve for each gas individually, and that gives you the partial pressures of each gas individually, and then you just add them together, it gives you the total pressure. Any questions on that there? The major contributor to pressure here is which one? Which one's causing more pressure? Which one has the greater partial pressure? Helium, yeah, it's got 12.3 atmospheres versus 2.44 atmospheres, right? So the one that's actually causing the most pressure here is actually the helium in that mixture, followed by the neon. Any ideas why that might be? It has to do with these numbers here. Helium is much lighter, which means it will be moving much faster. So helium is flying around a lot faster, causing more collisions, which is why it's contributing to a lot more pressure than the very slower moving neon, which is not moving around as fast, causing less collisions and causing less partial pressure. So, you know, how fast the gas moves is related to its weight. So lighter gases move a lot faster than heavier gases, they move a lot slower. Any questions on that there? So this is one type of partial pressure situation. Another type of partial pressure situation is a situation like this. Maybe you did. I don't know. Bad memories, this one. All right, so you put something like here, a little potassium chlorate, you heat it up in your test tube, has a little MnO2. You did this experiment, yes? Yeah. Did you dump enough of that in there, or did they just give it to you now pre-mixed? Yeah, did you put a bunch of it in? Manganese dioxide, yeah? Yeah. Well, if you didn't put a lot in, you probably were there for a while. You got to put a lot in, probably, I imagine, yeah? Wow. Glad I wasn't there, I suppose. All right. Yeah, that's really a catalyst. So they used to years ago not tell you to put a lot in. So people would just put a little bit in and they'd be like, I don't see anything happening and stuff like that. So, all right. But as you do this, what actually happens in this reaction, as you witnessed, hopefully, is it will decompose into potassium chloride and make some oxygen gas, which is what you were interested in. When you did this and you heated it, the O2 had nowhere to go. So it followed the path of least resistance. It came through here where you had a bucket of water filled with it. And as the oxygen gas bubbled in, the water escaped, right? And what you were left with was this nice empty spot here, which really wasn't empty, right? It did have your, in this particular example, your oxygen gas. Now, the process of doing this experiment here, we are collecting it over water. And when you do that, just the process of the heat of the reaction, when heat and water get together, you also collected in there some water vapor. Yeah. So you get some water vapor that was collected in there, which is the gas version of water, obviously. And in this situation, you actually have a mixture of two gases. And in most situations when you would do this, you're really not interested in the water. You're actually interested in this case, like the oxygen gas is actually the one that you get. So in a situation like this, the total pressure is equal to the pressure of the gas you're interested in plus the vapor pressure of water, which is what that is referred to. And that usually is a value you can look up on a table based on the temperature. And this is another sort of partial pressure problem where simply, if we were interested in just the partial pressure of the gas here, partial pressure of the gas would be the total pressure minus the vapor pressure of water. In the lab situation, once again, that total pressure would have been your barometer reading, and the vapor pressure would have been something that you look up. So a lot of times when you do some type of collection of a gas, which is a very common procedure, you take water and you basically have the gas displace the water in the container and you collect it that way. You always get this sort of mixture of gases. And like I said, in most situations, you're really not interested in the water part of it. So you have to sort of subtract it off. Sometimes they refer to it as getting the pressure of the dry gas because you subtracted off the water is sometimes how it's referred to. So in this situation, like we just did there, if a sample of oxygen gas is saturated with water vapor at 30 degrees Celsius, the total pressure is 753 torr, and the vapor pressure of water at 30 degrees Celsius is 31.824 torr. What is the partial pressure of oxygen? So what this problem is describing is basically the picture we just talked about where we collected the water. How do you know it's this type of situation in a book problem? Well, it usually says something like this. It's saturated with water vapor. It will sometimes say you collected the gas over water. So some mention of water vapor, some mention of collecting your gas over water basically tells you it is that situation, and you have to use pretty much this equation, the vapor pressure of water, basically. So in this case, we do have the total pressure given to us, which is 753 torr. We are looking for the partial pressure of oxygen gas. And again, this would be a table value that you would go look up at. So that's why it's giving you the 30 degrees, because you would go to the table and look up 30 degrees, and it would tell you the vapor pressure of water is this number. So that's what those temperatures are really there for. It's really not putting it into any formula here. So that tells us when we look it up there, it is 31.824 torr. So the nice thing about this type of partial pressure problem is it's really just subtraction. So to find the partial pressure of O2, 753 torr minus 3.1, 31.824 torr. There we go. And if we do that, that tells us that just the pressure of the oxygen gas in this case, which is what we're interested in, would be about 721 torr. And that again would be sometimes referred to as the dry gas in this situation. And we do want it in atmospheres. So what should I do with that number to get it to atmospheres? That is where our 760 comes into play. We would divide by 760 torr is 1 atmosphere. The torrs here will cancel, and that would give us 0.949 atmospheres. So this type of partial pressure problem, not too bad. It really does end up being sort of a subtraction type problem. And again, this is always a situation that occurs whenever you collect a gas over water, which again is a very, very common laboratory practice. And like I said, in book problems, that is what you're looking for: saturated with water vapor, collected over water, something in that situation. That is going to be this type of partial pressure problem. Any questions on that there? All right, so to finish up here, the kinetic molecular theory of gases. These are some of the important parts of the kinetic molecular theory of gases, a lot of which we kind of talked about throughout this chapter. Gases are obviously tiny particles that are atoms or molecules. The second thing here is, again, what makes something an ideal gas, and it's the idea that these particles are so small that compared to the distances between them, that the volume of the gas itself is basically negligible. It's basically thought to be zero. So again, that's why in a lot of gas problems that you come across, they really do refer more to the volume of the container rather than the volume of the actual gas, because in an ideal situation, the volume of the container is actually really important. So this thing here is one of the things that makes something an ideal gas. The particles are in constant motion, colliding with the walls of the container. These collisions are with the walls of the container are what again causes the pressure that we associate with gas. And as we talked about, as the collisions increase, we do expect the pressure to increase with it. And as the collisions of the gas start to come down, we expect the pressure to start to come down as well. Number 4 here as well is the second thing that again makes something an ideal gas. And that is the idea that it is assumed in ideal situations that the gas molecules flying around are not attracted to one another. They're not repelled by one another. And that is why, like the problem we just did with the partial pressures, we're able to do each gas individually, even though they're in the same container, because even though they're in the same container in an ideal situation, there is really no interaction between them. If there was interaction between them, it would affect things like pressure, because they would kind of slow down because they're attracted to each other as they're supposed to be just free to fly around freely. If there was some type of attractive force, again, it'll create some drag and it'll cause the collisions perhaps to come down. But in an ideal situation, we don't have any of that. And lastly, the average kinetic energy of a gas particle are directly proportional to the temperature in Kelvin. So as we talked about, as you increase the temperature, we see the gas molecules move a lot faster, and vice versa. If you lower the temperature, we will see the gas molecules really kind of slow down. Here are some of the relationships we talked about in those gas laws. As I just mentioned, higher temperatures, faster moving gas molecules going to hit the container a lot more often, and definitely in a sort of Guy-Lusick situation where the volume is fixed, we will definitely see the pressure increase, and vice versa. If you lower the temperature, we have less collisions, and we'll start to see less collisions with the container and the pressure come down. As volume and temperature, again, the way that Charles' law works, as we talked about, the volume does adjust to maintain the constant pressure. So that's why when we see the temperature rise in a Charles law situation, the volume arises accordingly to maintain the pressure. And as the temperature comes down, so does the volume as well, to maintain the constant pressure. Any questions on any of that stuff there? Looks good. That is the end of chapter 8, which, as we discussed today, is on this exam. And that is the end of the material that's on the upcoming exam, which will be in 2 weeks.